For more than a century, scientists believed our ancient world was home to just two kinds of humans, modern Homo sapiens and the Neanderthals. That story felt complete until a fragment of bone no longer than a fingernail shattered it forever. Just 12 millimeters long, a tiny finger bone pulled from a remote Siberian cave revealed an entirely lost branch of humanity. Its DNA would rewrite human origins, link a mysterious jawbone found on the roof of the world, and expose a legacy still shaping living people today. Who were the Denisovans, and how far did their shadow really stretch? The bone that changed everything. In 2008, deep inside Denisova Cave in the Altai Mountains of southern Siberia, archaeologists uncovered an unremarkable fragment of bone. It came from the pinky finger of a young girl who had died tens of thousands of years earlier. At first glance, it seemed insignificant, just another fragment among many. But this tiny bone would soon upend everything scientists thought they knew about human evolution. The specimen was sent to Leipzig, Germany, to the Max Planck Institute for Evolutionary Anthropology. There, geneticist Svante Pabo and his team prepared it for analysis. Their specialty was extracting ancient DNA from remains most scientists considered hopeless. They began with mitochondrial DNA, which survives longer than nuclear DNA. As the sequences emerged, the team realized they were seeing something extraordinary. This genetic code did not match modern humans. It did not match Neanderthals. It belonged to a lineage that had split off nearly 1 million years ago. Published in Nature in 2010, the results confirmed the existence of a third kind of ancient human, one that had lived alongside both Neanderthals and our own ancestors. They were named Denisovans, after the cave that hid them for millennia. A humanity known by molecules. Unlike Neanderthals, who left behind hundreds of bones and partial skeletons, the Denisovans were ghosts. They were known only from fragments, a finger, a few oversized molars, and later, scattered pieces of bone. Their physical appearance remained a mystery. To fill the gaps, scientists turned to DNA methylation patterns, chemical markers that influence how genes are expressed. These patterns suggested Denisovans likely had dark skin, brown hair, and broad faces, but the evidence was indirect. An entire branch of humanity had been identified not by skulls or tools, but by molecules extracted from a sliver of bone. Even more astonishing was their genetic diversity. Denisovan DNA showed greater variation than all sequenced Neanderthals combined, suggesting they had lived across vast regions and for long periods of time. But where exactly had they lived? The jawbone on the roof of the world. The next major clue had been hiding in plain sight for decades. In 1980, high on the Tibetan plateau, a Buddhist monk searching for relics in Baishai Karst Cave discovered a massive weathered jawbone buried in sediment. The cave sits more than 3,200 meters above sea level, where oxygen is scarce and even modern visitors struggle to breathe. The monk handed the jawbone to local authorities. It was placed in a museum, its true identity unknown. Nearly 40 years later, researchers from Lanzhou University and the Max Planck Institute re-examined the fossil. DNA had not survived the harsh conditions, but scientists turned to something more durable: proteins. Using collagen fingerprinting, they extracted molecular fragments from the bone's mineral core. Collagen can survive for hundreds of thousands of years, and it carries evolutionary signatures. The results were unmistakable. The proteins matched those from Denisovan fossils in Siberia. Dating placed the jawbone at least 160,000 years old, making it far older than the famous finger bone. This was the first Denisovan fossil found outside Siberia, and the first from extreme high altitude. Even more striking, modern Tibetans carry a gene, EPAS1, that allows them to thrive in low-oxygen environments. That gene came from the Denisovans. Long before modern humans arrived, Denisovans were already masters of the roof of the world. The face of a ghost, Dragon Man. Yet one mystery remained unsolved. What did a Denisovan actually look like? The answer lay buried for nearly a century. In 1933, a laborer building a bridge near Harbin in northeast China unearthed a massive human skull. Fearing confiscation during foreign occupation, he hid it in an abandoned well, where it remained concealed for almost 90 years. Only after his death did his family reveal the skull to scientists in 2018. The cranium was enormous, broad-faced, with thick brow ridges and a powerful build. Some researchers proposed a new species, Homo longi, nicknamed Dragon Man. Others suspected a connection to Denisovans, but proof remained elusive. That proof came from an unexpected source: dental calculus, hardened plaque clinging to the skull's teeth. In 2025, scientists extracted mitochondrial DNA from the calculus. After testing dozens of samples, a handful yielded usable genetic material. The results were definitive. Dragon Man's DNA clustered tightly with Denisovans, especially older specimens from Denisova Cave. At last, the Denisovans had a face. What began as an act of quiet defiance by a laborer had solved one of paleoanthropology's greatest mysteries. Mapping a lost world. Today, sediment DNA is rewriting the Denisovan map. In caves across Asia, from Tibet to Laos, scientists are finding Denisovan genetic traces preserved not in bones, but in soil. At Baishia Cave, sediment layers revealed Denisovan DNA spanning more than 50,000 years. In Southeast Asia, protein analysis of a single tooth confirmed their presence deep in tropical forests. Even where fossils are absent, their genetic footprints remain. One of the most extraordinary discoveries came from Denisova Cave itself, a hybrid child born around 90,000 years ago, whose mother was Neanderthal and whose father was Denisovan. This single bone is direct evidence of interbreeding between ancient human groups, a genetic crossroads that shaped all of us. The legacy in living blood. Denisovans are not just part of prehistory. People in Melanesia and parts of Oceania carry up to 6% Denisovan ancestry, the highest known today. In Tibet, Denisovan genes regulate oxygen levels in the blood, allowing millions to live where others cannot. Their DNA still breathes in human lungs, still pulses through human veins. Denisovans did not vanish without a trace. They became part of us. As ancient molecules redraw the boundaries of humanity, one truth endures: our origins are still being written, and every fragment, every grain of soil has the power to change who we think we are. What do you think the Denisovans still have to teach us? Share your thoughts below.